How to modify cheap China desktop CNC machine to get a confident 10 mils repeatable tolerance PCB milling. In this video I will disclose basic modifications needed to convert a budget China desktop 3020 CNC into professional grade PCB milling machine. But first let's inspect the final result achieved. This is my final test and I'm happy with the result. You can see there is a 10 mils or 250 microns track test board. I took this reference from real Texas Instruments engineers designed PCB. It is professionally designed industry standards PCB, and let's inspect a little bit its final result. This is my maximum zoom what I can make with my camera, still having sharpness, and you can see on the top it's a depth of cut. I did 3 versions of cut depths to understand which one is confident and reliable, and you can see that 0.05 millimeters depth is sufficient for a perfect usage, and but also this little bit more deeper 0.06 and 0.07 is still usable. Also those are good actually, but for reliability I would say 0.05 is optimum in my case at least. Let's inspect final result under a microscope. There are several ways how can we estimate quality, and one of them is how good are squares, because each time when we are changing directions by 90 degrees or 45 degrees, all errors are visible. Either we have thinner tracks or other artifacts. And here you can see all those track thicknesses are perfect. Practically there is no movement errors, and that means the ball screws are very good. So chosen solution is great. Second one, let's estimate what is a final summed error, and here is I think thickest part of the mill. I'm using 100 microns mill or 0.1 millimeter 30 degrees mill, and roughly estimating I would say that total runout of spindle collet, clamp, collet nut, and the tool is around not 30-50 microns. No, that's mean plus minus 50 microns is 100 microns because it's rotating. I would say it's a very good result, and that means I simply can define that my mill using this 0.1 millimeter mill. I can define that it is 0.2 millimeter mill. It includes all errors, and I have a confident result out of it. I did it in this way, and you can see outcome is perfect. Let's compare with the photoresistive method. Also here is a great confident result, and absolutely useful for a 10 mils PCB, but you can see that track confidence, some variations, so etching errors, roundness of pads, variation of pads is much larger, and I would say that milling process has a higher confidence than photoresistive. Of course there are errors of film and errors of printer which is making film, but anyway, slight modification of really hobbyist CNC machine gave fantastic result. Let's come back to our milling. Yes, fantastic, and those squares. Okay, here is 0.05 depths. How about 0.06 depths? Absolutely confident, the same. All those pads are square. How about 0.7? Yeah, here is 0.7. Of course, track thickness is reducing, so we are going deeper. That spaces are larger, but tracks are smaller. But still, absolutely confident, perfect result. How about when the tools start to wear out? Okay, here is, let's take this 0.05, and here is another the same. And practically we can see the wear out of the tool. So it is perfect. In a real life, you can see here between SMD pads, there's a copper, and you should remove it. That means I need a second pass, and I decided that I will do it with the same tool. I don't make any changes that could impact my result. I just run another file and define the tool is 0.4, and then it takes a longer distance away from the pad, from the contour, and then I remove copper here. Of course, it will not go deeper here where the space between tracks are too small, so that second pass will work only on the places where I have more copper. Those large copper places will stay, but I don't care about it. I keep it as a part of the process, that I'm not cleaning all the PCB. Except special cases when I need something for high frequencies, because then such kind of pads on a dual sided PCBs, those are capacitors, then I clean everything. But those are special cases, and then we decide how to make and what to do, and maybe we will use another tools, and it's not a standard case. About the quality saying, especially when working with those modern communication frequencies, there are type of the filters, and filters based on a stripes on a substrate, on a Teflon, or on a fiberglass, and you can see I can do such kind of filters with relatively high confidence. Better with than with etching. Of course, anyway, when you are building filters, then you work with a laser or just with a scalpel and take away some materials and tune those filters. But anyway, you can do initial patterns and then measure, tune, and make a lot of things out of it. So I would say that this particular case I succeeded very much, and the quality is outstanding. Could I do smaller or a higher tolerance, like 6 mils? Theoretically I can. Practically I don't see any meaningless scenario where I need it. So what is the conclusion? We are making photoresist method obsolete, or for special cases, and moving to the new method. We are moving to PCB milling. Fantastic result. I'm really happy. About the tool, which tool to choose? There is one thing. Since we are milling fiberglass, the equivalent material of fiberglass is sandpaper, and that means those tools are wearing out pretty quickly, and it could be great if you can use some really budget tool, and it's small budget tool, smallest and cheapest end mill possible. You can buy, I don't know, 20 pieces for $10, and with one such kind of tool you can mill high complexity dual-sided PCB, and then it's become unsharp. If you have simple complexity PCB, you can mill about 10 PCBs. I would say the price is neglectable, also in favor of PCB milling.